Hi guys, coming to you today from my little home basement makeshift whiteboard. Sorry the quality's not going to be the best on this one. Hopefully I'm going to try to write really big. I have this whiteboard at home, so I just decided to try to use it, but my webcam is not the best. So 1.3, there's relatively just two topics we kind of have to talk about with 1.3, and this is one of them. And we'll do another topic right after this, and that'll be it. So first we need to talk about the increasing, decreasing, and constant functions. So basically this is just writing an interval using the x values to say what is happening with the function from one point to the next. So the example I have up here is just, this is a flat line right here. I'm not the best at drawing that, but it's a flat line. You'll see this is kind of a swoop to a flat line up to another swoop going back up. So you should know it's the exact same thing as slope. So if you think about a decreasing slope, that's the same thing as a decreasing function, right? When it's starting up high and going right low. Constant is obviously where we have that flat horizontal line. It's remaining constant from one to the next. And then increasing is going to be when you start low and go high to the right, okay? So when we're talking, where is this function decreasing? Again, we use our x values for our x coordinates. So if we look over here at -5, between -5 and all the way until it gets to -2, it's on this decreasing slope. So that's going to be the interval of decreasing. Then you'll see between -2 and +2, we have this kind of constant flat line. Right, I'm not going up, I'm not going down, I'm just remaining right along this value of y equals 3. So that's going to be the interval -2 to 2 for remaining constant. So in the place that my function is increasing is going to be from this 2 all the way out here to 5. Okay, that's how we get that 2, 5 interval. It's just as easy as that. There's not a lot that goes into that, but it's something worth touching on. Because you're going to see that vocabulary used often. Okay. So if you're doing honors, you'll be doing the piecewise functions. If you're not, then we're not doing them like as a regular class. The next thing is talking about even, odd, or neither functions. So just like we need to know the terms of when we're increasing, constant, and decreasing for functions, we also need to be able to recognize when they're even, when they're odd, or when they're neither. Quite honestly, neither is probably the more common with functions that get a little bit more nasty, but we do sometimes have an even and odd, and that's terms that we use to help describe and solve anything to do with those graphs. So I'm going to put some examples up here. Sure. Okay, so what I want us to do for all 4 of these graphs is determine whether or not they're even or odd. So you'll need this set of kind of definitions for even and odd functions. So if a function is even, you could fold it, okay, over top of the y-axis, right? Fold it over top and it would match up. Okay, so the more technical definition of that would be that it's symmetrical along the y-axis. Okay, again, you could fold it over the y-axis and it would be symmetrical. So then with odd functions, this is going to be that it's symmetrical about the origin. So what I like to say is that I could put a pin on the origin and I could flip this function around about 180, 360, anything, and it's going to match up. Okay, so when we look at this first one, we need to figure out whether or not it's even or odd. So when I'm looking at when I'm seeing this is that this looks exactly like what's happening on that side, almost like it's mirroring each other, right? So if I were to fold it over this line, it would match up, which is the definition of an even function, okay? Even is symmetrical about the y-axis. This is identically symmetrical about that y-axis, so therefore that function is an even function. So when we have an odd function, it's because it's symmetrical about the origin. So if I put my finger right in the origin of this function, and let's say I twisted it, it's like 180. So I brought this part up to here, and I took this part down to there. It would match up identically, right? I could just flip this around once, twice, 3 times, every single time, it's going to match up. That means it's symmetrical about the origin or an odd function. Okay, so you can kind of start seeing that you're not going to have odd functions all that often. You're probably also not going to have even functions all that often because we just don't have functions that are that perfect, that go through the origin and match up on both sides, or that kind of play off this y-axis, even and symmetrical on both sides. It's not something that happens incredibly often, but in this chapter we kind of make those things happen to make you able to see them. So looking over here at this one, remember we have that neither option. It's going to happen. So we test it. Am I symmetrical about the y-axis? Could I fold this in half over that y-axis and it would match up? Definitely not. The majority of this parabola is on the right side. So if I folded it up, it would not match up at all. So this is going to be a neither. Okay, last one. When you're looking at this parabola, it doesn't go straight through the origin. So my guess is it's probably not odd. Okay, I'm not going through the origin, so it'd be hard to flip me around it and me still be able to be symmetrical. So then start thinking about, well, is it even? If I folded it over top this y-axis, it would in fact match up. So it is even. Okay, that's how you tell even and odd by looking at its graph. Now, we can also determine even and odd functions by using algebra. Okay, so I'm going to do a little bit of notation here for you. A function is even when you take the original function, f of negative x, and it comes out as positive. Okay, we'll talk a little bit more about what this notation means in a second. So then it is odd when, again, you take f of negative x and it comes out to be negative f of x. Okay, be super careful where you're seeing these negatives, right? Right out in front, there's a negative here and a negative here. Okay, so I'm going to kind of talk you through this by using an example. I want to know, is the following function f of x equals x cubed minus 3? Or x cubed minus x, sorry. Odd, even, or neither. Okay, odd, even, or neither. That's a really bad question mark. Okay, so what I have to do, both of these notations start out that I have to take f of negative x. So we talked a little bit about taking, what was my word for it? Composition of functions. Okay, so we talked about substitution before. So now instead of substituting like f of 3 or f of 7, this time I'm taking f of negative x. So every single place I see an x, so right here and right here, I have to add in a negative right in front of it. And I like to do that in parentheses. So here's me testing. Okay, I like to put that down. I'm testing f of negative x. So let's say every time I see an x, I put a negative x, but I need to put those parentheses around it because I'm using a substitution. So it's subtracted from another x, so I add in another negative x. Okay, so you can see you replaced x, negative, making a double negative here. Anytime we cube something that is negative, okay, that's the same thing as saying negative x times negative x times negative x. Two negatives make a positive, positive and negative makes a negative. So when your exponent is odd, it's going to remain negative. When it is an even exponent, it's going to turn that positive. So this remains negative x cubed. Now we have a double negative, so subtracting a positive, or subtracting a negative makes adding a positive. So now I have negative x cubed plus x. So my first test, if my function, when I put in a negative x, came out to be my exact identical function, then it's even. Okay, so the function I put in was, right, I had to put a negative, but the original function was x cubed minus 3. X cubed minus x, I don't know why I keep saying that. So does that match up identically to what I have down here? No, because my signs are different, right? Both of them are different. So it's not odd. This step tells me, not odd, it's not even. I don't think I can talk tonight, I'm sorry. This step tells me that it is not even. Now I want to test, well, is it odd? So that the odd notation is that when I put in a negative x, it will come out to be that I can factor a negative out, and what's left on the inside matches up to my original equation. So let's try doing that. We need to factor out a negative, okay? So when you factor something out, it's the same thing as dividing by that. So I'm dividing by basically a -1 and a -1. Negative divided by negative makes a positive. Positive divided by negative makes a negative, okay? So I have my negative here on the outside. Does what's on the inside now match up to my original function? Yes, I have a positive x cubed, minus x, minus x. So this tells me yes, odd. Okay, so I'm not going to do another example. If we need to do one in class, I will. What I will tell you, oh gosh, I'm really close, I'm sorry. So what I will say is what would have happened if this would have said no, it's not odd. I would have done nothing else and said, okay, that means it's neither, and been done. Okay, so if you get a yes here at even, you're done. If you get a no, you keep going on to check to see if it's odd. If you still get a no, you just say, okay, it wasn't odd, it wasn't even, so that obviously means my last option is neither. Okay, again, like I said, if you need more examples of this, I can do more in class. I don't want to keep this video going any longer though than it already has. So those are basically the two big things about talking about just graphs and functions, is dealing with when they're increasing, decreasing, and constant, and then when they're even, odd, or neither. Okay, that is all for this time.